SUMaC 2022 SUMaC Stanford University Mathematics Camp. There are 8 problems. We want to work on the 8 problems of SUMaC. So at first let me tell you, if you wanted the next videos, also the next solutions of any summer camps and another competition, something like this, for having next videos, subscribe my YouTube channel, turn on the bell to notice, and like my videos. If you wanted more explanation about the solutions, my WhatsApp number is this, and also my mail is this, but WhatsApp number is better, and I would check that earlier. So let's start problem number 1. The problem number 1 is, as the problem says, an open-ended question. So you can say any property of this number 2022. For example, you can prime factorize the number 2 times 3 times 337, multiplication of 3 prime numbers, and you can say 2023 is 7 times 17 squared, so 2022 is 7x squared minus 1. So you can say, for example, it is 4x squared minus x squared minus 1 squared. So it is, you can reach by adding 2 squares and then subtracting 2 other squares like this. You can find any good properties. So as the problem says, open-ended question. So let's go to problem number 2. Problem number 2 says a number n has the increasing factor property if it can be uniquely factored into a product of strictly increasing factors, not including the factorization n equals 1 times n. So you can't consider 1 times n, so you reject 1 and n, and as the problem says, n is product of n1 times n2 to nk for k greater than 1, and 1 is strictly less than n1 less than n2 to less than nk less than strictly less than n, and there is no other factorization. N equals m1 to ml with, so the rest of the problem, with again that property such that m1 m2 to ml is different than the sequence n1 to nk. For example, so let's consider the example of the problem 6. If you consider 6, the divisors are 1, 2, 3, 6. So as the problem says, if you want to select n1 to nk, 1 and n are not permissible. So you cross 1, cross 6, so the only possible divisors are 2 and 3. You should select at least 2 of them. K is greater than 1. So for 6, you can say, okay, 6 equals 2 times 3. And the problem says uniquely, so only one way should be possible. So 6 has the increasing factor property. Let's read the rest of that. The problem explains here, and there are no factorization of 6 with strictly increasing factors. There are no other. Now 12 does not have this property since it can be factored into strictly increasing factors in 2 ways. So when you want to consider 12, you write the divisors 1, 2, 3, 4, 6, 12. And as you can see, we can't select 1 and 12 because of this condition and this condition. And also you should select at least 2, k is greater than 1. So one way you can say 2 times 6, one way you can say 3 times 4. So 12 doesn't have the increasing factor property because you can write it in 2 ways. It must be unique. So 12 doesn't have the property, but 6 has a property. Now, for solving this, I would tell you the last answers. Suppose P is a prime, R is another prime, which P is not equal to R. For this problem, only 3 types of problems are good. So PR has the increasing factor property. It is the first one. The second one, P cubed, has the increasing factor property, and P to the fourth has the increasing factor property too. And All other numbers except these three types don't have increasing factor property. You should prove it completely. Checking these numbers are not hard. For example, let me tell you PR. You can say the divisors of PR are 1, PR, PR. You can select these two, so the only way is P times R. Also, let me tell you P to the fourth. If you write the divisors, it's 1, P squared, P cubed, P to the fourth. And 1 cross P4 because you can't select 1 and N. So if you select P squared, you should multiply it to itself. The problem says N1 is less than N2. You can't select a divisor more than once. So you here, the only way to write P to the fourth is P times P cubed. Also, similarly, we can prove P cubed is good because it can only be right like P times P squared. So these three types of numbers are the only numbers that you can prove. Any other number except these numbers doesn't have any other number don't have increasing factor property. Let me explain, for example, some of them for you. If you have P, for example, squared R cubed and P is not equal to R, then you can say, okay, it can be equal to P times P, R cubed equals to R, P squared, R squared. So for any number, but you should generalize and you should, it was just considering some cases, but you should prove the whole number. And now, for more explanation and complete proof, you can call my WhatsApp number or email, but WhatsApp number is better. I can explain completely for you. It was problem number 2, so I said exactly the answers are what? These 1, 2, 3, but whole proof, as I said, you can call or send message through my WhatsApp number. Now, let's go to problem number 3. Find a polynomial p of x with integer coefficients for which 2 root 3 plus 3 root 2 is a root. That is, find p of x such that for some positive integer n and integers a0, a1, a2 to an, p of x equals a0 plus a1x plus a2x squared plus 2anxn, and p of 2 root 3 plus 3 root 2 equals 0. It's because of the roots. So let's consider this one. For this problem, it has two conditions. One root, an integer coefficient. So one polynomial is it. If you want to know, it has also, there are infinitely many polynomials that satisfy these two conditions. But there are many ways how to find them, how to reach them. If you want to know how to find them, how to reach them, as I said, you can send message through my WhatsApp number. So here, I consider p of x equals, but I prove now this polynomial works. So it's x to the fourth minus 60x squared plus 36. So I replace x with 2 root 3 plus 3 root 2. It would be 2 root 3 plus 3 root 2 to the fourth minus 60. Let's replace x again with 2 root 3 plus 3 root 2, 2 root 3 plus 3 root 2 squared plus 36 equals. So the first one squared 4 times 3, 12. Second one squared 9 times 2, 18. Plus 2 times first one, second one, 2, 2, 4, 3, 12. Root 3, root 2, root 6. Again squared because it's to the power of 4. Minus 60. This is squared. Again, exactly similarly, we can say 12 plus 18 plus 12 root 6 plus 36. Now, let's simplify. Again, we know it is 30 plus 12 root 6 squared minus 60. 12 plus 18, 30 plus 12 root 6 plus 36. Now, 30 squared is 900 plus 12 root 6 squared. It's 144 times 6 plus 2 times this root 6. 2 times 30, 60, 60 times 12, 6 times 12 is 72, so 720 root 6 minus 60 times 30 minus 1800 minus 60 times 12 root 6, so it would be minus 1700. As I said here, you can say 6 times 12 is 72 and 0, 72, 0 minus root 6 plus 36. So if we simplify, we can see 720 root 6 negative. They would be cancelled. And so if I want, let's go through the problem. So if we simplify, it would be what? 900 plus this one. So if we simplify, let's check case by case. 900 plus 6 times this plus 7. I've written all the things here, so we cancel these two things, and now 900 plus 6 times this would be 864 minus 800 plus 36. 900, this one plus this one, it would be again 900 minus 1800 equals 0. So as you saw, this polynomial works, and we found one polynomial, and the problem wants find a polynomial. It doesn't want us how we reach, but you should know how to reach to answer this problem. Okay, let's go to problem number 4. Problem number 4, let me select this. Okay. It says, let's go through the problem. Consider a stack of 5 blocks in the following arrangement A, B, C, D, E. Suppose you are allowed to rearrange the blocks according to the rule that any 3 blocks that are touching each other can be rearranged as follows. If the 3 blocks X, Y, and Z all touch each other, then block X can move to the position of block Y can move the position of block Z, and block Z can move the position of block X. We call this kind of rearrangement a cycle. For example, in the starting configuration above, we can cycle ABD. Okay, you can cycle clockwise, counterclockwise, because here, as you can see, XYZ, the problem doesn't say that only, for example, in one direction. You can consider XYZ like this, or XYZ counterclockwise or clockwise. So we have all 2 directions. So cycle A, B, C, D, E to obtain this. So let me explain. C is here. It doesn't change. E also doesn't change. The only thing, A goes to B. So the direction is clockwise. A to B, B to D like this, and D to A. And then in the second cycle, we can rearrange D, B, and C here. So D, B, and C. So A and E are here. Their position didn't change. So D here, let's see, again clockwise. D goes to B, to the position, B to here, and C to here. So it was the definition of the problem. Is it possible to obtain this from A, B, C, D, E? So the answer of the first part is yes. Is it possible? The answer of second part is no. So the first part is easy. It needs to only tell an example. So here, A, B, C, D, we want to reach from A, B, C, D, E to E, D, C, B, E. So at first consider the cycle. A, B, D clockwise like this. So C and E and their place don't change. So here, as you can see, B comes here, D here to A, this position, and A to here. Okay, it's clockwise. Now, in this place, consider D and C are in the same place, but consider cycle around A, B, E. Again, clockwise. A here, E here, as you can see, and B here. And in the third step, consider B, D, E. A and C are in the same place. B goes to E, E to D, and this place D to B. So We've proved the first part with an example, but in the second part, the part B is harder. You should prove that it is impossible. Let me give you a hint. From A, B, C, D, E, you can go exactly. If we want to count all the arrangement, there are 5 factorial, which is 120. 120 is all of the arrangements, and we can prove from A, B, C, D, E, you can go through 60 arrangement, but BACDE is in another 60 arrangement. So if you are in here, you can go to any of the arrangement here. If you are here, you can go to any arrangement of here. It has a proof, and if you want it, I can prove it. As I said, you can send message through my WhatsApp number for the whole proof here. Here the topic, you can define something that is constant here. For example, something has some property here, and in this place you don't have exactly that property, and say okay, always we have that property, and you can't reach it. It's a combinatorics problem, and the idea of these topics, this kind of problem, all of them are invariant. Okay, it's problem number 4. We said A is yes, we consider the example, and part B we said no, and therefore we said why, and we work on the hint for, and as I said, for complete proof of this part, send message through my WhatsApp or email, but WhatsApp, as I said, is better. Problem number 4 was that. Problem number 5. Consider the following game. Okay, let's read the problem completely. Here it says, consider the following game. You are given a sequence of the letters A, B, C, D, and you are given the following replacement rules that allow you to replace some combinations of letters with different combination of letters. The first, second, third. First one. 2 distinct adjacent letters among A, B, and C can be replaced with the third. More formally, X, Y can be replaced with Z, where X, Y, and Z are distinct elements of the set A, B, C. For example, if X is C, Y is B, Z A. So by this rule allows CB to be replaced with A. So you can replace 2 adjacent CB to A, or AC to B, or BC to A. And the arrangement is not important. CB or BC, both of them, you can change to A. ABC can be replaced here. One only permutation is possible. Only ABC, not CBA, not BCA. Only ABC. 1 from 6 arrangement of ABC can be replaced with the only ABC adjacent. And the third part is the above rules can be reversed. For example, C can be replaced with AB, and D can be replaced by ABC. So you can replace ABC by D or replace D by ABC. Now the problem, let's read once what from us. As an example of a round of play in this game, consider the starting sequence CBA. In the first move, we can use the third part in combination with first part to replace C with AB. So if you replace C with AB, it would be AB, and you write the rest of that BA. And now here, then in our next move, we can use first part to replace BA with C. So you can replace BA with C, so it would be ABC, which can be replaced with D, because ABC, here we said ABC, you can replace it with D using second part. And now, in the third move, prove the following. Part A, for X equals A, B, C, or D, X, X can be replaced with D in a series of moves. So let's at first consider part A. When it says X, X, and X can be A, B, C, or D, so we have 4 cases. AA, BB, CC, DD, and with D in a series of moves. Okay, so you can replace AA with ABC, and how? You consider this part, you change this A to BC here, and then here ABC is obvious how to reach D. For BB, consider each of them, change each of them to AC and AC here, and then change, for example, CA to B, and A and C we have, so ABC to D. For CC, change the first C to AB, then ABC to D. For D, consider each of them ABC, ABC. Now, and then change CA to B, so it would be A, B, 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 C, and then you can change these. Let's see what we've done on this BC. You can select, and it would be A, B, B, change it by A. And the last part, select this and replace BA with C and ABC to D. So we proved part A completely here. So let's read part B. In part B, the problem says for X, A, B, C, or D, the pairs X, D, and DX can each be replaced by X in a series of moves. Okay, so X can be A, B, C, or D, X, D, and DX. So if you replace X with A, D, DA, we should prove that we can reach X. Here X is A, so in each case AD and DA, we should prove that we can reach A and A. And also X can be B, C, or D. So B, D, D, B, C, D, D, C, D, 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 D are same, so you need to only check D, D. And in the first part, part A, we proved D, D, you can reach D. So you can copy and paste D, D from first part. Now let's consider AD, DA, BD, DB, CD, and DC and prove part B completely. Okay, AD, consider D here. A we had, D replaced with ABC, and then we replace AB with C, so it would be ACC. And then you can replace AC with B, so it would be BC, and then you replace the whole BC with A. So the first part we proved. Now DA replace D with ABC, and then replace CA with B. So we have A, B, B. Now replace AB with C. CB, now replace the whole CB with A by the assumption of the problem. Now BD, replace D with ABC, so it would be BABC. Then replace BA with C, and then BC we have. The next part, replace BC with A, and you have C here. And then replace AC with B. Okay, so we proved also BD. Now let's the time for DB. Replace D with ABC, and you have B here. Then let's see, replace BCB with A. So it would be ABA, then replace BA with C, so it would be AC, and then replace AC with B. So we've proved 4 from 7, because also I said it is in part A, it is okay. So 2 cases are left, C, D. Replace D with ABC. So it would be CABC. And then you replace, let's check, you replace BB, okay, so you select CA and it would be BBC, then you replace BC with ABA and C. For DC, replace D with ABCC, replace D with ABC, and DC is for DC for DC. And then you select BC, you change replace BC with A, it would be AAC, and then replace AC with B, it would be AB, and then replace AB with C. And now here you have 2 Ds, replace each D with ABC, ABC, and then if you select BC with A, and you can select, let's see, you replace this BC with A, so it would be AAA BC. Then you replace this AB with C, it would be AACC, and then you replace this AC with B, it would be ABC, and then replace it with D. It was in part A also. Now, the hardest part is part C. It has the problem. Let's see, the problem says what? Show that for any given starting point sequence, there is exactly one letter among A, B, C, D, E, ABCD that can be reached through a sequence of moves. So here you should prove that you can reach one letter, and also you should prove that that letter is unique because of exactly. I would prove that why you can reach one letter, but for the whole proof that why that letter we have reached exactly that letter and that's unique, for the whole proof you should send message through my WhatsApp number or email. And I said WhatsApp is better. So at first let me tell you how you can reach one letter. So when we consider the string, the adjacent letters can be AA, BB, CC, DD, or AB, AC, BC, or AD, BD, CD, and DD. Let me tell you something. Here we said AB. Also, if you have BA, it is not important. CA, BC, CB, AD, DA, DB, DC, and also DD. So all the cases are these. Okay. So if you see AA, by part A you can reach D. Part A was what? Here we proved AA, you can reach one letter. So if you have AA, you can reach one letter D. If you have BB, also you can reach one letter D. If you have CC, one letter D by part A, DD by part A. AB by the assumption of the problem. The problem says AB to C also. You can reach from BA to C. Similarly, the problem says AC to B and CA to B. BC to A, CB to A, and AD in part B, we said you can change it to B. Let me show you. AD, DA, we proved we can reach A, so we can use that. Part A and B were useful for part C. So, AD to B, DA, you can also change it by part B, you can reach A. Again, by part E, you can reach A. DB or BD, you can reach by part B to B. For CD also, you can reach C. Sorry, here I should erase it. CD, you can reach C. And DD, you can reach B. So we considered all the cases also we had DD. So we can't, because in one case we part A we prove, one case we part B. One of them is enough. So we prove the two adjacent, if you consider two adjacent letters, in any case I can change it to one letter. So you can do it again and again to reach only one letter, but why that letter is unique? It is harder than all the other parts. And as I said, if you wanted the whole proof why it is unique, so you can send message through my WhatsApp number, as I said in the first of the video. So it was problem number 5 and we proved problem number 5 completely. Let's solve problem number 6. Problem number 6, let's read the problem. Consider the following puzzle. You are given a 4x4 puzzle board, this with 4 kinds of tiles to be used as puzzle pieces. So this one, this one, this one, this one. The arrows on these tiles point up left, the first one, down right, this one, down, up left, up right, okay, up left, up right, respectively here, down right, down left. For the purposes of this problem, we consider each arrow to point toward a corner as well as toward the two neighboring edges of that corner on the tile. For example, on the first tile above, the arrow is considered to point to the upper left corner here, upper left corner, it arrows to upper left corner. The left side also, it arrows to this one, not this one. Cut. Okay, so upper left corner, so this corner, and the left side, this one, not this one. So, and also the top side. So this side, not this side, because it arrows to these two sides and this corner. You are given as many tiles, so here also it doesn't arrows, only top and left. You are given as many tiles of each type as you may need, and the goal of the puzzle is to fill the squares on the board with these tiles according to the following conditions. The first condition, arrows on neighbor Neighboring tiles, that is tiles that touch each other on an edge or on a corner, cannot point toward the adjoining shared edge or toward the adjoining shared corners. For example, the following are not allowed. So let me explain each of them why. The first one, because both of them point to this side. This one, again, both of them point to this side. And also you could say to this corner. But we can also say side. So this side, they arrow to this side, and in this case, only to this corner. So they are not allowed. And it says in A and B, there are a common, let me change the color. In A and B, there is a common edge. In A and B, common edge, where one arrow points up to that edge and the other arrow points down to that same edge, which is not allowed. In C and D, the arrow points right and left to the same edge here, the edge, which is not allowed. And in A and D, E, A, D, E, the two arrows point to the same corner, which is not allowed. Okay, here, as it says here, also the corner is here. But if one of them happens, then it would be bad. Each row is required to have two tiles with arrows pointing up and two tiles with arrows pointing down. And each column is required to have two tiles with arrows pointing to the left and two tiles with arrows pointing to the right. For example, the following are not allowed. So it says what? Each row have two tiles. So in each row you have two up and two down. So two up, two down, and in each column you have two right, two left. Okay, so let's see. Here, the first part, let's consider the row is this row is bad because 4 up. This row is good, so this row is bad. This row is good. This row is good. This row is bad. This row, this column, 2 left, 3 left, 1 right, so it is bad because it must have 2 left, 2 right. 2 left, okay, 3 left. Again, this column is also bad. Right, right, left, right, okay, 3 right. This column is also bad. Right, 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 okay, this column is bad. What about this one? 2 ups, 3 up, okay, 1 down is bad. 2, 3 up, 1 down is bad. 1. If we consider 3 downs, 1 up is bad. 3 downs, 1 up is bad. Now, what about the column? We consider rows. So 4 up, 4 left is bad. 2 left, 2 right is good. This column, 2 left, 2 right, this column is good. 4 right, this column is bad. Now you've understood. It says in A, the first row has all 4 arrows pointing up, and the fourth row has all 4 arrows pointing down. As I said, the first and last row is bad, of which are, and neither of which are allowed. And in B, the first column has all arrows pointing left. Okay, the first column is bad. The fourth column, as I said, has all arrows pointing right, so neither of which are allowed. Does this puzzle have a solution satisfying both condition first and second? Yes. If so, how many distinct solutions are possible for this puzzle? 2. Explain carefully how you know the solutions you have accounted for, if any, are the only one possible. Okay, so guessing and finding the answer is not easy. But if you guess many cases, maybe you can reach the answer. But if you solve it by only guessing, for example, if they want to consider your mark, if it has, for example, 10 marks, you would get at most 1 or 2 marks. But the important thing is what to prove why that 2 cases are the only good cases and why there are no other good cases. So I would tell you only the 2 good cases if you wanted the whole proof for this part, that why we don't have any other good cases, because the problem, as you can see, the problem says explain carefully how you know the solutions you have accounted for these are the only. This is the hardest part of this, and 80%, at least 80% of the mark of this problem is this. So if you want exactly the proof how I've reached only these two good examples, you can send message through my WhatsApp number, as I said in the first of the video, and also you can read in the description. So here, We have 2 ups, 2 downs in the first row. It's okay. 2 ups, 2 down, 2 up, 2 down, 2 up, 2 down, 2 left to right, 2 left to right, 2 left to right, 2 left to right. And as you can see, they don't point to a same edge or same vertex. Here again, this row, 2 up, 2 down, 2 up, 2 up, 2 down, 2 down, 2 up, 2 down, 2 up. This column left to right, to left to right, to left to right, to left to right. And also if you see, for example, this arrow pointing to up and left, and this corner, no other arrows pointing to this side or this side or this point. So these are the only 2 good answers. We can prove there are only these 2 good answers for this. We don't have any, and we can prove that. Okay, so as I said, for whole clue, send message. So the next one, problem number 7. Let's consider problem number 7 of SUMaC 2022. It has 2 parts. The first part is so much easier. The second part is harder. So let's read it. In this problem, we consider some 2 sequences of numbers. That is a finite sequence of positive integers that starts with 1 and where each number that comes later in the sequence is the sum of 2 previous numbers, including the possibility of adding a number to itself. For example, 1, 2, 4, 8, 16 is a sum 2 sequence where each number is obtained by adding the previous number to itself. Also, 1, 2, 3, 5, 8, 13 is a sum 2 sequence. Why? Because look, the problem says each element is addition of 2 previous elements, or you can add an element to itself. So for example, 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, 8 is 3 plus 5, 13 is 8 plus 5. Also we have another one. The next one is 1 plus 1, 3 is 1 plus 2, 4 is 2 plus 2. You can add one element to itself. 5 is 2 plus 3, 6 is 4 plus 2, or 5 plus 1. It is not. You can select both of them. Okay, so it's sum to sequence this one where after adding 1 to itself, each number is a sum of the 2 previous. It is Fibonacci sequence, is a special case of sum 2 sequences. Okay, the following is also a sum 2 sequence, as I explained, obtained by starting with 1 and adding 1 to each to get each successive number. More formally, a sum 2 sequence is a sequence of integers n1 to nk for k greater than 0, such that n1 is 1, and for r2 to k there are s and t such that s and t are previous terms less than r. They can also be equal, and nr is ns plus nt. We call k the length of the sum 2 sequence. So here, for example, the length is 1, 2, 3, 4, 5, 6. And for this one, 1, 2, 3, 4, 5, 6. The length here is 6. The length here is 6. For each positive integer n, we can look for the smallest k. It is important such that there is a sum 2 sequence ending in n. For example, we can get n equals 10 in the sequence 1, 2, 4, 8, 10 with k equals 5, and it is not possible to get 10 in a shorter sequence. So the minimum length is 1, 2, 3, 4, 5. Since the maximum value of n with k equals 4 is 8, because the first one is 1, the second one is at most 2, 1 plus 1. The third one is at most 4, 2 plus 2, 4. And this one is at most 8, 4 plus 4. So with 4 elements, you can't reach 10, because the last one, the fourth element, is at most 8. Now, we understand the problem completely. Let's solve part A and part B. Note that 1, 2, 4, 8, 16, 32, 48, 50 is a sum 2 sequence for n equals 50. Let's consider. 2 is 1 plus 1, 4 is 2 plus 2, 8 is 4 plus 4, 16 is 8 plus 8, 32 is 16 plus 16, 48 is 32 plus 16, and 50 is 48 plus 2. And the length is what? 1, 2, 3, 4, 5, 6, 7, 8. The smallest k for n and says show that 8 is the smallest k for n equals 50 by showing no sum to sequence of length 7 ends in 50. We try to prove it by contradiction. Suppose that we can reach with length 7. At first, let me tell you something. We know n1 is 1, n2 is at most 2, n3 is at most 4 because n2 plus n2, n4 is at most 8, n5 is at most 16, and 6 is at most 32. So, but n7 is at most 64. So until here, we can prove easily that the length 6 is impossible because the greatest number is 32, and now we want to reach 50. So suppose we want to prove by contradiction. Suppose the 7th element is 50. 1, 2, 3, 4, 5, 6, 7. Now, we know it is what? It is n. It is, if we consider n, show that 8 is the smallest, so by contradiction. n7, it is n6, it is n5. Now, n4, I know n7 is 50, and if you add n6 and n5, it's 16 plus 32, 48. We can't reach 50 by n5 and n6. So we should only use n6. So you should add n6 plus n6 equals n7. So n7 is 50, it is 2 n6. So n6 has to be what? 25. Now again use the same proof, it's 25. If you want to add n4 and 5 to reach n6, so 8 here, 16 here, 16 plus 8, 24. You won't reach 25. It's 1 less than 25. So the only case for n6, similarly, would be n5 plus n5. We proved n6 is 25. So it is 2n5. The left side, so n5 is 12.5, contradiction. So, or you can also say it is even, this part is odd. So even cannot be equal to odd because n5 is an integer. So that's a contradiction. We proved part A completely now. Part B. What is the length of the smallest sum to sequence for n equals 55 in addition to showing that your value of k works for n equals 55? You need, this is the hardest part, you need to prove there are no smaller values of k that also works for n equals 55. As we said, we know n1 is at most, it is 1, n2 also 2, n3 at most 4, n4 at most 8, n5 at most 16, n6 at most 32, and n7 is at most 64. So because it is 55, easily we can say the length is at least 7. So the answer can be, length can be 7, 8, and 9. And all these things are, why I say until 9? Because we can say example 1, 2, 3, 5, 6, 11, 22, 44, 55. Why is good? 3 is 2, 1, 5 is 3, 2, 6 is 5, you can say 1, 5, or 3 times 2, 11 is 5, 6, 11 you can multiply, 11 plus 11, 22 plus 22, 44 is 11 plus 44, 55. The length is what? 1, 2, 3, 4, 5, 6, 7, 8, 9. So because we found the length with 9 and we want to find the smallest one, as the problem says, so the answer is 9 or less than that. We proved the answer cannot be 6 or less than that, so the only possible cases are 7, 8, and 9. So with 9 we can write in many other good sequence, sum to sequence. So 9 is good. Now you should reject 7 and 8. 7, rejecting 7 is easy, but rejecting 8 is not easy at all. So if you want to know the proof of 8, why we can reject it, the answer is 9. The answer is 9. If you wanted to know how we can reject 8, as I said, you can send message through my WhatsApp number. My WhatsApp number is in the description of the video and also in the first of the video. So here I told you the answer 9, and I said you should reject what, and for the whole proof you can send message. Now let's go to problem number 8. Last problem. The problem says, let's read the problem. For the following, let me select this. Okay. For the following Sudoku style puzzle, you are given the following 9 by 9 grid. Okay. And you need to fill it in with zeros and ones satisfying the following conditions. So first condition, each row, each column, and each red or blue 3 by 3 box must contain exactly 2 ones and 7 zeros. No 2 ones can be in squares that touch horizontally, vertically, or diagonally. For example, the following is a solution to this puzzle. So as you can see, in this column we have 2 ones, 2 ones, 2 ones, 2 ones, 2 1 in this column here. For this column, these 2 ones, these 2 ones, 2 ones. So all the columns are okay. If you check the rows, the first row 2 ones, 2 ones, these 2 ones okay, these 2 ones okay, 1 and 1 okay, 1 and 1 okay, 1 and 1 okay, 1 and 1 here okay, and 2 ones okay. If you consider each 3 by 3, the first one has only 2 ones, exactly 2 ones, okay. It says each 3 by 3, each row, each column. Now we are checking 3 by 3, 2 ones, 2 ones, okay, okay, it's okay, 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 2, 2, 2. And here is okay. And no 2 ones can be in squares that touch like these 3 ways. If you check 1, all, it means that all around. In general, if you have 1, 1, all 9, 1, 2, 3, 4, 5, 6, 7, 8, all 8 cells around that must be 0. And you can see all ones are okay. This one, okay, all cells around that are 0. Okay, so we proved also second part now. However, the following is not a solution, although it satisfies condition first, the highlight one on in the second solution. This one, it says it is not a solution. Why? We want to check that. So it says okay, these 2 ones are adjacent. Okay, so it is, we can reject it by that. The first part A, it has 3 parts, A, B, C. Now let's focus on part A. In the following version of the puzzle, 2 squares in the center, 3 by 3s, 3 by 3 region have ones on corners like this, across from each other diagonally. Show that it is impossible to fill in the blank squares on this puzzle satisfying conditions first and second. Okay, so let's see why. In this case, it is first part. Let's fill it. Let's fill first part. Let me check. This part. Okay, part 1, part A. We have 2 ones here. We know, for example, this is 0. You can say that if I want, let's fill it from the first part together. So let me tell you something. It is important and you can use it in part B and C. Centers are 0. Because if in one center you have 1 all around, that must be 0. And then in this 3 by 3 we need 2 ones. There must be 2 ones, but here it would be 1 1. So you can use it in all 3 parts. All the centers of the 3 by 3s are 0. So you can place it like this. And now we have 2 ones in this 3 by 3. So you can say, okay, this 3 by 3, all other cells are 0. This one, adjacent cells, 0. Adjacent also, if they have, the problem says in the assumption, if they have 2 common points, if they have 1 common point also, they are adjacent. So it is 0, it is 0, it is 0, it is 0, and also this one is 0, this one is 0. Now the other thing you can say, if you consider this row, it must be 1, it must be 1. And because it is 1, it is 0, 0, all the adjacent are 0, 0, 0, 0, 0. Then you can say here we have 1, here we have 1. Then you can say, okay, because this is 1, then this is 0, this is 0, adjacent to this one, 0. Because you have this one, it is 0, 0, 0. And let's see what else we can say. Okay. So also we know this center is 0. If you consider this column, we need 2 ones and only 2 cells are left. So they must be 1, 1. So if you place this one 0, 0, 0, 0, and this 3 by 3, we've reached contradiction because it has exactly 1, 1. But the problem says in each 3 by 3, 2 ones. The second part. The second part, you can't solve it with one way. You should consider on some places. For example, consider the cases of something, and it depends on you. It is not only a special case. Or solve it with many different ways. You can consider cases of anything, and in all the ways I've reached 6, and I know the answer is exactly 6. So if you wanted to know, also I can solve it with the way you want and reach again 6. If you wanted how we reached 6, so I said the last answer, but if you want to know how we can reach 6, you can send message through my WhatsApp number that is in the description or also in the first of the video, or email. Now, let me tell you the last part, part C. This is harder. You should use part A and part B for solving this. And reaching 68 is not easy. But I can show you how you can reach this answer, 68, for part C. If you wanted to know how we proved the answer is 68, not less, not more, exactly 68. As I said, you can send message through my WhatsApp number and also email in the description or the first of the video.